So now we have punched a tiny little pinhole in the car, and we're aligning the reflection from the concave mirror with the hole.
So, what was going
We adjusted the tip and tilt of the concave mirror until it was perfectly aligned, and now we can see the red laser light. And now we can see the mode structure.
And if we rotate the polarizer, we can see that they disappear, so that tells us that they are in fact linearly polarized. So inside this interferometer, we're creating resonance at the modes of the laser, and only those signals are coming out in any appreciable volume. And what we're getting here is these nodes from the laser. And so taking the distances between these, because this is a time measurement, we can figure out the frequency separation in the modes.
The result is a mode separation of 912.7 megahertz. The percent error here is very large because our theoretical value is based off of a complete guess for the cavity length.
In this case, we're measuring the frequency, and we're just measuring it as intensity peaks as a function of time based on the resonance that we get out of this interferometer, versus the optical spectrum analyzer there is measuring the wavelength of the light. And so it would appear this is a little bit more accurate, because we're actually able to distinguish between the modes just a little bit better, I think, than that one over there. What we're doing with this is we're measuring the central wavelength of the laser, the number of modes, and the mode distances if any. In this case, there's a single mode. The central wavelength is right about 632.8, like we would expect for a key laser. And then what we're going to do next is replace it with the laser diode, and we're going to measure the spectrum of this as well.
For the helium neon laser, we found a central wavelength of 632.8 nanometers and a full width half max of 43 picometers. The laser diode had 8 modes, and you can see on screen the central wavelengths and the full width half maxes for each one. We found an average mode spacing of 175.8 picometers.
We can see here on the oscilloscope where there's a separation between like peaks. That's 10 gigahertz in the interferometer, and so we have a time separation here. We're going to use that time separation to figure out a configuration factor to then take a measurement of the secondary modes inside of those peaks.
So first we aligned the laser with the photodetector, and now we're going to adjust the starting frequency so that it doesn't catch that first peak.
And we'll do a peak search. And there she is, right there.
There she is. Using the ESA, we found a mode separation of 883 megahertz. Again, we have a large percent error because our theoretical value was based off of a guess for the cavity length.